Welcome to 2.7 Similarity Theorems and Proportional Reasoning. So in this lesson, we're going to go over the shortcuts to determine if triangles are similar. Remember when we talked about congruent triangles, we needed shortcuts, or we used shortcuts to determine whether triangles were congruent without needing to know every single measurement. So in this lesson, we're going to do a very similar thing, but instead of congruent triangles, it'll be similar triangles. So for that, let's review what we call the cross product. Now it's called a cross product because you would cross multiply as such. So what would that give us? That would give us 4 times 6 equals to 3 times 8. See how we just crossed it over? Okay, that would give us 24 equals 24. Now, you mainly use this when you're going to be solving for some unknown, such as x. That would be our unknown variable. So how do we do it for this situation? Same thing, cross multiply. So you get 5 times x equals to 1 times 50. That is simplified to 5x equals 50. Now we want to solve for x, and we need to get x by itself. So we divide by 5, and we solve, and we get x equals 10. Okay, so we're going to be using that in this lesson to solve for sides, unknown sides. So let's practice using this example. Given that triangle ABC is similar to triangle DEF, find x. Now remember, what does it mean to be similar? Remember that similar triangles are proportional. That means the ratios for their corresponding sides are equal to each other, right? So let's identify corresponding sides. So DE is a side, and it corresponds to AB. AB. Okay, and this will give us some number, and it's some ratio. Remember, we called it the scale factor. And this ratio is going to equal the ratio for another corresponding side, right? And that corresponding side would be EF. So EF corresponds to BC, right? Why did I write this? Because DE and AB are corresponding sides, and they will give some ratio. And that ratio will be equal to the ratio given by these corresponding sides, where EF corresponds to BC, okay? So now we can fill in what we know. DE is 18, AB is 6, equals to EF, which is x, our unknown, and BC is 8. Doesn't this expression or equation look a lot like what we just went over up here? Yes, it does. So see how we took what we learned from last lesson and set up an expression so that we can solve for some unknown, some missing side. So again, we'll just use the cross product property. So 18 times 8 equals to 6 times x. Okay, and 18 times 8 is, I don't know off the top of my head, that is 144 equals to 6x. Again, solve for x, and 144 divided by 6 will give us 24. So our missing side is 24. Okay, so understanding how to set this up and then how to solve for x using the cross product will allow you to solve for a missing side. So now before we get into the shortcuts to determine similar triangles, I want to remind you of the shortcuts we used to determine congruent triangles. Remember, we had 3 postulates. We had the side, 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 angle, side, angle, side, angle. And remember, we asked if we can have alternate forms such as angle, 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 side, side angle, and angle, angle, side, where for these two, the angle and the side would not be included. And we determined that these would not work because they do not guarantee congruency, so only these 4 would work. So in this lesson, we're going to see if we can have a very similar form and apply it to determine similar triangles, okay? So first is the angle-angle similarity postulate. This states that if two angles of one triangle are congruent to two angles of another triangle, then the two triangles are similar, okay? It could be these two angles, it could be these two angles, or it could be these two angles. It doesn't matter. Now you can think about why this works. Remember the theorem where if two angles of one triangle are congruent to two angles of another triangle, then the third angle is also congruent. And remember, what did we discover about similar triangles? They had congruent angles and proportional sides. So that's why the angle-angle similarity postulate works. Again, it's just stating that if you see two angles congruent to each other in two triangles, then they are similar. Next theorem, side similarity. So this states that if the lengths of corresponding sides of two triangles are proportional, right? So lengths of corresponding sides for two triangles, if we see that they are proportional, then the two triangles are similar. Remember, what does it mean to be proportional? Their ratios have to be the same. So we see 7 corresponds to 14, 5 corresponds to 10, 8 corresponds to 16, and if we simplify all of these, we actually get 1:2 ratios. Therefore, the corresponding sides, all three, are proportional, so these two triangles are similar. Now, it's important to keep in mind that all three sides have to have the same ratios. If 2 out of 3 only have the same ratios, then it's not similar. If it's only 1 out of 3 sides, then it's not similar, okay? So all three sides the lengths of all three sides need to be proportional in order to be considered similar triangles. Now let's get into the third one. Side-angle side similarity theorem. This states that if an included angle of one triangle is congruent to an angle of another triangle, and the two lengths of corresponding sides are proportional, then the triangles are similar. So this third theorem is very similar to the second one, except instead of having a third side, you would just have an angle. And remember, it's an included angle, so it needs to be included between the two sides. And you can see that here because the angle is sandwiched in between the S's, which stand for sides. Okay, so first, the angles are congruent, and they are included. Now, the two sides, the lengths of the two sides are proportional because 5 corresponds to 15, 3 corresponds to 9, and if you simplify both of them, you get 1:3 ratios. So these two lengths are proportional, and the angles are congruent. So because of that, they are similar triangles. Now let's look at an example. Are these two triangles similar? Well, we are given 3 sides, so you should automatically think side, side, side. And what does the SSS theorem state? It states that if the lengths of the 3 sides are proportional, then the triangles are similar. Let's check. 6 corresponds to 12, 7 corresponds to 14, 5 corresponds to 15. What does this simplify to? 1:2. What about this? 1:2. And what about this? This actually simplifies to 1:3. Since the ratios are not the same, then they are not proportional. So these triangles are not similar. Now we're going to get into an example where we need to prove similarity. Remember, we were proving congruence using what was given and what we learned about previous relationships with angles and also theorems. So same thing, we're going to prove similarity. So first, it states that segment AB is parallel to segment DE. We can see that it's given in the figure by those arrows. So here's our statement, and we're going to write given. Oops, that should not say proofs, that should say reason. Okay, what else do we know? Well, we know that DCE, this angle right here, is actually congruent to angle BCE. Now, how do we know that? Remember the vertical angle theorem. So we can write angle DCE is congruent to angle BCA. And the reason is the vertical angle theorem. Remember, the vertical angle theorem states that all pairs of vertical angles are congruent, and vertical angles are on opposite sides of each other. What else do we notice? We notice that angle E is congruent to angle A. And why? I should use a different color. No, hang on. Angle E is congruent to angle A. How do we know that? We know AB and DE are parallel. So if we continued on as parallel lines, we notice that AE is a transversal and it's cutting through these parallel lines. And what kind of relationship, what special pairs of angles did we learn? One of them was alternate interior angles, where they're on the inside of parallel lines and they are alternating, so they're on different sides of the transversal. Okay, so another statement is that angle E is congruent to angle A. And we know that because of the alternate interior angle relationship angle when we see a transversal cutting a pair of parallel lines. Okay? Now can we conclude similarity? Well, you see that we have two angles that are congruent to two. Okay, sorry. You see two angles of one triangle that are congruent to two other angles in another triangle. And remember, that is actually the angle-angle similarity postulate. So now we can actually conclude that triangle ABC is similar. This is the notation for similar. Is similar to triangle EDC. And again, what is the reason? It's because of the angle-angle similarity postulate, where two angles of one triangle are congruent to two other angles of the other triangle. Therefore, they are similar. Okay? Now let's get into another example. Are these triangles similar? If so, which postulate applies? Well, right away, we see we're given two sides and one angle, okay? Now, what does this remind you of? This reminds you of the side angle side theorem, where one angle is congruent to another angle for two triangles, and the sides are proportional, okay? So we can see already that they are congruent based on the arcs and the value of the angles. Now we have to check if the lengths of corresponding sides are proportional. So 3 corresponds to 9, 7 corresponds to 21, and if we simplify, we get a 1-to-3 ratio, 1-to-3 ratio, and since these are the same, then so we see an angle that is congruent and two sides that are proportional. Therefore, these are similar triangles, and the postulate that applies, or theorem, is the side angle side theorem. Let's just say which postulate / theorem. But yes, these two triangles are similar because of the side angle side theorem.